What are harmonics, and how do we create specific frequencies of sound, such as in music? These are the questions students explore in Investigation 16D, Resonance and Sound. This investigation has two parts. In part one, students use tuning forks to explore standing sound waves inside a pipe and the different physical features that cause the system to resonate, just like a musical instrument. Students also explore how a wine glass resonates in part one. In part two, students measure the frequency of a plucked guitar string at different lengths along the fretboard and make connections between the physical properties of the string and the sound waves generated by it. In your software, open the 16D Resonance and Sound experiment file. In the file is a graph of intensity versus frequency. Students use this graph to measure the frequency of the sound generated by their tuning fork. Start recording data and then strike the tuning fork and hold it near the microphone on your computer or tablet. Click stop once a clear peak is formed. The tallest peak represents the frequency of sound generated by the tuning fork. Students record this frequency value in Table 1 in their handout. Strike the tuning fork over the tube and then raise or lower the tube in the water reservoir until it begins to resonate. You'll know it's resonating when the sound from the tuning fork is amplified. Measure the length of the tube above the water at resonance and then record that value in Table 1. Students will repeat this same procedure for two other tuning forks, tabulating their data in Table 1. Students should recognize that tuning forks with lower frequencies require a longer tube to resonate, that is, a longer piece of tube above the water. This is because the wavelengths of the standing waves in the pipe are longer. For the second half of part one, wet your finger and rub the rim of a wine glass until it starts to resonate. Students will measure the resonant frequency using the same 16D experiment file. Then, students measure and record the dimensions of the wine glass in Table 2 in their handout. Students will then fill the wine glass with different amounts of water and record the different resonant frequencies at each water depth. Students will find that the resonant frequency decreases as the glass fills with water, which implies that the length of the air column in the glass does not have the same effect as it did with the previous open pipe. In part 2, pluck one of the guitar strings and measure the frequency of the sound wave generated by the string. In the graph, students should record the frequency of the first peak. This represents the fundamental frequency of the string, or the frequency corresponding to a standing wave with wavelength equal to twice the length of the string. Students record the length of the string and the fundamental frequency it produces, and then repeat the same procedure for different lengths of the same string. Students change the length of the string by pressing it onto the guitar's fretboard at different frets. Students then repeat the same procedure for additional strings and plot their data in the graph in their handout. Graphs of frequency versus length should show an inverse relationship, as frequency is inversely proportional to wavelength, and length in each trial is equal to the wavelength divided by 2. The same graphs for different strings should look similar but shifted in the graph due to the difference in wave speed between strings. Different strings have different mass per unit length, which changes the speed the waves travel in the string.